Hello everyone, my name is Hamid Alian and I'm a MSc student in the Department of Electrical and Computer Engineering in the University of Alberta. The title of my presentation for today is Multi-Agent Asynchronous Maze Searching. Our work is focused on multi-agent field searching because using multiple agents highly affects the time consumption challenge in a task. Two examples of multi-agent field searching applications in the real world are rescue operations and exploration robots. Main challenge with working on multi-agent systems is how to manage their collaboration to perform a task which is in common for all agents. In our case, this task is maze searching. Now I define the problem which I want to solve. We consider an m by n grid maze and k agents distributed around the maze and occupying different cells. We assume that agents do not know the geometry and position of the obstacles and the way to exit at the beginning. Our main objective is to implement a hierarchical decision-making process for each agent, such that the group of agents can collaboratively explore the maze and sharing the information with other agents until all agents reach the goal cell. Before stating the solution, we begin by describing the shared map, which contains the information shared between the robots as they move through the maze. Each agent maintains a real-time copy of the shared map and the number of times it visited each vertex. In the shared map, a white cell is a cell that has not yet been visited by any agent. Before the exploration begins, all vertices representing the cells in the shared map are marked as white cells. A gray, a gray cell is a cell that has been visited by an agent at least once. A black cell or dead-end cell refers to a cell that is surrounded by either obstacles or other black cells in three of its boundaries. An OC flag or occupation flag is a true or false flag associated with each vertex used to represent when vertex in the shared map is occupied by an agent. OC flag indicates that the respective cell is occupied or is empty. Figure 1 describes the effect of a robot moving between two cells and the OC flag. We divide our solution onto two main phases. In phase 1 of the solution, each agent follows these rules until one agent finds the destination. At any arbitrary state, an agent identifies the obstacles in all four directions using its distance sensors and contributes the sensed obstacles to the shared map. Next, the agents choose an adjacent cell with a false valued OC flag to move by the following order in case of availability. First priority is white cell. Second priority is gray cell. If there is more than one, then the agent moves into the cell that has been visited the fewest times by the same agent. If there exists only one way to exit from the current cell and all other directions are obstacles or black cells, the color of the current cell has to be changed to black, and then agent chooses exit way. In this case, if the OC flag value of the exit way is true, the agent waits until the OC flag reverts to false. In phase 2, each agent calculates the shortest path to the destination in the shared map and moves toward this path until reaching the destination. In general, common path planning algorithms use a sequential algorithm, meaning that commands are executed one by one. In this scenario, agents cannot move simultaneously, meaning that whenever an agent is moving, all other agents must wait. Although effective, this type of algorithm results in a slow solution of the maze. But our main goal is to complete the algorithm in a non-sequential manner, meaning that executing the algorithm in such a way that all agents are allowed to move simultaneously. To accomplish this objective, we define a thread function associated with each agent and execute the algorithm in all threads in parallel rather than sequentially. This video is a simulation of the algorithm with real robots. On the left side of the video, we have the visualization of the robot's shared map. You can see that how the colors of the cells change according to the rules. In conclusion, we tested the algorithm for a 10 by 10 maze by 3 robots and the algorithm worked well. But for now, we do not have the complete set of statistics to show the performance of the algorithm. For example, tests for randomly generated mazes and different number of robots, which we want to work on in the future. Thank you everyone for listening to my presentation and let me know if you have any questions.